Okay, well, welcome back. We'll have one last video here on Chapter 8 and Lewis structures, and we've kind of gone past the end of the notes at this point, but I do just want to maybe clarify and bring up a couple other examples, some things on the handout about drawing Lewis structures we should look at. Let me start with kind of a continuation of this idea of formal charges. I made a chart earlier looking at carbon, nitrogen, oxygen, fluorine as the representatives of compounds that have a certain number of valence electrons, but we were limited in that chart into thinking of the octet rule as we're only trying to get to 8 electrons. It is important for us to think about for the larger elements. So if we go down from those elements that are limited to 8, right, carbon is limited to 8, we'll only have 4 bonds. Silicon pretty generally is also only going to have 4 bonds. We don't really find a situation with valence electron number 4 where you'd add 5 bonds because you've already gone into a negative formal charge situation then. So silicon pretty much is just going to be like carbon. But nitrogen and phosphorus do have some differences. Oxygen and sulfur have some differences. Fluorine and chlorine have some differences. So let's explore those a little bit. So nitrogen, we said, is usually going to look like this. It's got 3 bonds, it's got a lone pair, and that gives it a 0 formal charge. Phosphorus can do the same though. So the difference being phosphorus is big enough to go past 8 electrons. This will also be 0 for phosphorus. So this would be 5 minus 3 minus 2. That would be a 0 formal charge for phosphorus. But because phosphorus can go past 8 electrons, we have another situation for phosphorus, in which case it can have a 0 formal charge as well, and that is 5 bonds to phosphorus. So this would be 5 minus 5. That could also get us to 0. So we should be on the lookout for both of those possibilities when we're considering bonding in a phosphorus compound, because either of those will be a pretty stable way for phosphorus to bond. If we think about oxygen, right, we said 2 bonds, 2 lone pairs, that gets us to 0 for oxygen, satisfies the octet rule. But sulfur, selenium, tellurium, the other compounds below oxygen in the column that has 6 valence electrons, have some other options. So let's look specifically at sulfur. So we could do exactly the same thing for sulfur. 2 bonds, 2 sets of non-bonding electrons, 6 minus 2 minus 4, that would be a 0 formal charge. But because sulfur can expand, the number of electrons it holds past 8 or past the octet, right, we might see a case where sulfur has 4 bonds and a pair of non-bonding electrons. So total of 10 electrons there, but 6 minus 4 bonds minus 2 non-bonding electrons, that would also be a 0 formal charge situation for sulfur. So another option we should consider when thinking about the bonding in sulfur is that we can go up to 10 electrons and still have a lone pair on the sulfur. Sulfur, right, and its lower in the column related elements like selenium and tellurium can also have 6 different bonds. So like we saw in the sulfur hexafluoride on the previous page. You give sulfur 6 bonds, that'd be a total of 12 electrons, but 6 minus 6, that would also be 0 for a 0 formal charge. So a few more options there in terms of bonding with phosphorus and sulfur and some of the larger elements. The same is true here if we get away from fluorine. So fluorine only can have 1 bond. Right? It can have 1 bond, 3 lone pairs. That's the only way we want to draw fluorine. But say we go down to chlorine, right? Certainly we could have the same thing. Chlorine could have 1 bond. It could have 3 sets of non-bonding electrons. That would be 7 minus 1 minus 6. That would be a 0 formal charge, right? But we can do some other things with chlorine too. Since chlorine can go past 8 electrons, we could have 3 bonds to a chlorine and then 2 sets of non-bonding electrons, right? That would be a total of 10 electrons, but formal charge-wise, 7 minus 3 minus 4, 0. Perfectly acceptable bonding situation for chlorine. Chlorine could also have 5 bonds, that's supposed to be 1 there. I drew it a little inexpertly. And a lone pair, 7 minus 5 minus 2 would also equal 0. Possible for chlorine, right? And we could even think of our halogens having 7. Different bonds. If you have 7 different bonds, 7 minus 7, 0 formal charge, right? Maybe to go all the way up to 14 electrons. It might be a little crowded on a chlorine, but you go down to a giant iodide, and you've got a lot of space around there where you could put extra electrons. So all those worthwhile things to think about if your central atom is, right, located again in the 3p block or somewhere below where it's a bigger atom. There's an opportunity to put more electrons around there. Okay, the other thing that I want to kind of mention here are some of the other things mentioned at the bottom of the Writing Lewis Structures handout. We already talked about expanded octets and how to watch out for that. The other things listed there at the bottom, one is incomplete octets. And the most common place we'll see an incomplete octet, particularly with a non-metal, is boron. I list beryllium and aluminum on the handout because sometimes their bonding is going to border on covalent bonding as opposed to metallic. But boron is the best example of a true non-metal that will do this here. If we think about boron, and we can think about a compound like BF3, boron and 3 fluorines. If we go to draw that, boron is less electronegative, so the boron would go in the center. We'd attach the fluorines to it. Right? A boron has 3 valence electrons. Each fluorine has 7 for a total of 24 electrons. We used 6 already, 18 left. That's just enough to complete the octets on the fluorines. Right, like so. Right? That gives an octet to each fluorine, gives a 0 formal charge to each fluorine, right? But we don't have an octet on the boron. But this is what we're on the lookout for. This is the most stable and the best representation of this molecule, just based on the fact that boron only brings 3 valence electrons into bonding, means in a lot of cases, boron is only going to end up making 3 bonds. And we don't want to make a double bond to fluorine. We've discussed that already. So there's no way in this particular structure to get the boron up to satisfying the octet rule. So it doesn't. This is the structure, and we just have 6 electrons on the boron in this structure. Now that may give us some information about how it's likely to react, right? That boron would be interested in getting some more electrons and getting to satisfy the octet rule, but often in the structure it is not going to satisfy the octet rule. So we would call that an incomplete octet, but that would still be the best structure for boron. Now notice it does have a 0 formal charge. 3 minus 3 would get boron to a 0 formal charge. So that is the best structure we can draw for boron. The only other thing mentioned at the bottom of the page there is odd electron counts. Now, if you have a single electron that's not paired up in an orbital, that is often referred to as a radical or a free radical, and part of that is related to the spin not canceling if you have a free electron. That is something we could encounter occasionally, and we really just have to apply our rules to that electron. So a fairly simple example we can think about is just NO, a nitrogen and an oxygen in our structure. And nitrogen has 5 valence electrons, oxygen has 6. So this would have 11 electrons. Now, in fact, every molecule we've talked about so far has had an even number of electrons. That is generally the rule. For the most part, if you have an even number of electrons, you can draw a good structure. If you have an odd number of electrons, you will always have 1 electron that is left out, right? It's 2 electrons to make a bond, 2 to make a lone pair. If you have an odd number, you're going to have 1 that doesn't quite fit in. So if you calculate and you get an odd number, you should maybe double check your calculation, right? But then when you're sure it's odd, then you just have to kind of draw the structure according to the same rules we've talked about. So in this case, right, you might just connect them in your skeleton, right? And that used up 2 electrons. That means we have 9 left, okay? Now, if I put them on the oxygen, that would only leave 3 to go on the nitrogen. So why might I decide to put the odd one on the nitrogen, right? A good thing to think about here is how many valence electrons would your formal charge calculation start with? Oxygen starts with 6. So if I have an unpaired electron on an oxygen, it's going to be hard to subtract 1 from 6 and end up with 0. But if you start with an odd number on your element and you subtract 1, then your pairs and your bonds could get you to 0 a little more easily. So an unpaired electron is more likely to end up on a nitrogen or a chlorine, the atom with the odd electron count, than it is on a carbon or an oxygen. Okay, so in this case, what we want to do is try to get as close as we can to satisfying the octet rule and having 0 formal charges. So I've got an octet on my oxygen here, but I'm shy of an octet on the nitrogen. I've only got 5. So I can't get to 8, but I can get closer if I make a double bond here. So if I make a double bond, I get this structure, 2 pairs left on the oxygen. So that's good. That's a 0 formal charge oxygen and satisfies the octet rule. And my nitrogen at least gets close. It gets to 7. So 2, 4, 6, 7 electrons. That's as close as I can get to 8 for nitrogen with this structure. But I did get to a 0 formal charge. So 5 minus 2 bonds minus 3 non-bonding electrons. So that is the best structure I can draw for NO. Now, just to verify, we might try, right? What if I reversed here and I put the even number on nitrogen and the odd number on oxygen? Where does that get me? Octet here, not here, share. Is that just as good as the other structure or not? Over here, I've got 5 minus 2 minus 4. That's actually a -1 for a nitrogen. Over here, 6 minus 2 minus 3. That's actually a +1 for the formal charge on my oxygen, and I still didn't satisfy the octet rule. I'm still 7 electrons here. So not only did I not satisfy the octet rule, but I got weird formal charges that I don't want. So this is not a good representation of the structure. This one was. Okay, so watch out for those, but you're really following the same rules and you're just trying to get as close to satisfying them as you can. That'll be the end of chapter 8. So stay tuned. We'll see some info from chapter 9 before too long.